Okay, so chapter 5 is all about energy. So far this semester, we have talked a lot about matter. Other than mentioning it briefly in the beginning of the semester, we haven't really talked a lot about energy. If you remember all the way back to the matter sort activity that you did with your group, where you just sorted a whole bunch of different items into pure and mixture, and within mixture you could either be homogeneous or heterogeneous, and within the pure category you could either be an element or a compound. I actually mixed in some things into that activity that were really energy. So something like thunder, for example, is sound, and sound is energy. Okay, so there are all different kinds of energies. If you watch the crash course video that I assigned, you got a few of those introduced to you already, but I bet that you could come up with a few more. All right, and so under this, what kinds of energy are there? I want you to fill some of these in. You should be able to fill in what is energy and what can energy do based on the crash course video. And of course, this question is kind of self-evident, but also based on crash course. And if you go into the presentation and you click on this link, it will open up a PhET simulation, and you can explore a whole bunch of other kinds of energy that are not talked about in the video. So I recommend doing that, and you can explore some of the things that we're talked about, like heat, right? And if you're cooling or heating something, that's all just changing the relative amount of heat. They are not different properties. They are two sides of the same coin. So this is exploring heat, and you can explore how phase change affects heat, which is something that is important in this chapter. But you can also click other systems. You can put in a bicyclist, you can put in a solar panel, all kinds of stuff. So use that and the crash course video to answer the questions on this slide. I recommend actually writing down your answers somewhere, either typing or whatever. All right. So just a reminder, some things that are going to be handy to remember. We know what molarity is. We learned about that in chapter 4. So we're going to use it here again, just like we did in chapter 4. This entire chapter is really about something called the conservation of energy, which is also known as the first law of thermodynamics. It just says that however much energy the universe has is all it will ever have, all it has ever had. It doesn't change. All right? And then in the crash course video, he introduces you to the idea of system versus surrounding. By the way, if you haven't watched that video, I'm kind of assuming that you did already, so you might want to go back, watch that, and then watch this one. All right, and so in chemistry, the system is very easy. It's the chemicals you're studying, and the surroundings are everything else, including the solvent, the container that it's in, the air around it, everything else that's not the chemicals, okay? We have 3 different kinds of systems. You can have a system where matter and energy can be transferred back and forth. That would be called open. You can have a system where only energy is transferred back and forth. So in other words, you put a lid on it so that like gases cannot evaporate and only heat can go back and forth. Or you can have a system where it is isolated, meaning no energy is transferred and no heat and no matter is exchanged either. So you have a lid on it and you have it in an insulated cup. When we do our calorimetry experiment, we use styrofoam insulated cups to try and create an isolated system. It isn't a perfect isolated system, but it's an attempt. All right, and then we got some other vocab words you're going to learn about. All right, and so I want you to think about these questions. Pause the video, write down an answer, what you think the answer is for each of these questions here, these 3. Okay, I'm going to assume you did that. I hope you did. It is much more instructive for you in your learning process to know what you already think before we talk about something. So the answer to the first question is essentially never. You are never going to create energy by breaking a bond. It's impossible. The thing to think about is simply that if a chemical has a bond, it's stable that way, okay, meaning lower in energy. And that means to break it, you're going to have to make it unstable, okay? So in order for any chemical change to happen, the first step is always breaking bonds, and you have to add a certain amount of energy to do that, right? And so we call this the activation energy. It's going to be up a hill. Here's our symbol for activation energy. This is essentially how much energy do we have to put in to break the bonds to get the reaction going. You get bonds back, you get energy back when you make new chemical bonds if they are more stable than what you started with, right? So for example, if this was our reactants, and these were our products, and this scale here is energy, and this scale here is time, right? And so if you start out with your reactants at some given level of energy and you have to put a little bit of it in to get it going, that's our activation energy. But then when you make new bonds, they suddenly are way more stable than the reactants you started with. That's when you get energy from the reaction. We call this kind of drawing an exothermic reaction. Exothermic means that heat is produced. Heat exits out of the system. Okay, so we're going to learn more about that in a little bit. It's not the only kind of energy exchange that might happen, but that is when you get energy back from making chemical bonds. The energy required to do a chemical reaction comes from the surroundings. Either you're adding it by heating up the reaction, or it's intrinsic in the air or the container or just the environment around the chemicals, the solvent. When a reaction produces energy, as we've sketched here, an exothermic reaction, it goes into the surroundings, right? It's going to go into the solvent or the container or the air that's around it. Your total amount of energy, though, is the same in the beginning and the end. Systems plus surrounding is going to equal whatever it started out at. All right, so I want you to think a little bit about kinetic energy. Kinetic energy is part of what drives chemical reactions. If you have high kinetic energy, then you're more likely to have things collide, which means you're more likely to get a reaction to occur. So I want to think just about this kind of on the scale of what we are familiar with on a day-to-day basis. So let's say I'm standing at the bottom of a hill, you guys are standing at the top of a hill. You have a beach ball and a bowling ball. If you roll them down the hill at regular gravity acceleration, right, which one do you think I am going to avoid if I have to pick? Yeah, obviously the bowling ball. It could probably break my shins, right, if it ran into me. But the beach ball is probably just going to bounce off and not do any harm. Okay. Now let's imagine the bowling ball does the same thing. Regular acceleration due to gravity. But the beach ball has an acceleration close to the speed of light when you roll it down that hill. Now which object should I avoid? Yeah, I'm going to avoid that beach ball if I can. If it's moving near the speed of light, I won't see it, but I'm going to try to avoid that one anyway, because anything moving near the speed of light, anything with substantial mass moving that fast, will cause immense amounts of damage. Do you know how much? There is a really good article by a physicist who writes comics, and the comics are called XKCD, and I will link them in our discussion board this week, because he did this what if that addresses this very issue. And the question someone asked him is, what if a baseball is thrown near the speed of light? And I think the answer will surprise you. So I'm going to go ahead and post that and you can read it for yourself. So we can draw a conclusion just based on this hypothetical situation about which one is more important in terms of energy, mass or velocity. And so our equation is kinetic energy is 1/2 the mass times velocity squared. The answer is that velocity matters far more than mass, right? Because the beach ball is much less massive than a bowling ball. But because it is moving faster and velocity is squared, that has a much bigger impact on the total amount of energy than the mass does. Another kind of energy we might encounter is electrical energy, all right? And this is from one of our 4 forces of nature, which is the electrostatic force. It says that like charges will repel each other, so positives and negatives. So 2 positive charges coming together, 2 negative charges coming together will repel each other, and it is dependent on the distance. So charge is represented by a capital Q. It's either a +1 or a -1 for chemistry. You could put Coulomb in there, but we don't mess with that until we get to the end of 142. This K is just a constant, and D is distance. So since you're dividing by the distance, the closer together the charges are, the bigger the energy will be. Whether that number is positive or negative depends on these terms, right? So if we have two positives, that's going to be a very high positive energy as they get close together. That is not favored. We call that a repulsion. They don't want to be there. If you have two negative charges, that will also be a high positive energy because, again, they repel each other. But if you have one positive and one negative, then you get a favorable interaction. You will get a negative energy. All right? That means you're getting energy back from that process. That means favorable. Okay? All right, and so these are the two kinds of specific equations we're going to talk about so far. Most of the time when we calculate a kinetic energy in chemistry, it's actually the kinetic energy of like an electron or an atom or something like that, gases. So that's why we're talking about this. We're not going to do a lot of calculation of really large objects in this course. Of course, obviously, electrostatic energy has a pretty big impact on chemistry because two things have to be oppositely charged to react with each other. Or have sufficient energy produced from making the bonds after a reaction to overcome this if they have the same charge. That does happen. These are not the only two equations in the chapter. Those are just the first two I want to give to you to begin with. Another fact that you should know about is the units of energy are a derived unit. That means we take our base units from chapter 1 and put them together. And so just to write this as a normal fraction, energy is mass times acceleration squared, right? So meters per second is an acceleration, and we're squaring that. So this is kind of derived from that same equation that we just looked at, right? So velocity is meters per second. You square it, and you multiply it by the mass. So as it turns out, the most common unit in chemistry is joules or kilojoules, which are derived from joules. And a joule is always equal to kilograms times meters squared divided by seconds squared because of how we define kinetic energy. And this is something handy to have, especially as you go on into physics, for those of you who are going to do that. All right. Another unit of energy that we use quite frequently is called a calorie. A calorie is defined as the amount of energy required to raise exactly 1 gram of pure water by 1 degree Celsius. That is a calorie. Now in science, a calorie is different from the calories on the back of a nutrition label. Nutritional calories are actually kilocalories, right? So remember that we can convert between like joules and kilojoules by remembering that there's 1,000 joules for every 1 kilojoule. So by extension with calories, there are 1,000 scientific calories in every 1 kilocalorie. Okay? So if I give you nutritional information, remember that. You've got to convert it from nutritional calories, which are kilocalories, into regular calories. Okay, I just want to show you, I found my child's stash of candy, and the way they get around this is by capitalizing the C on nutritional labels. You see how it's capital C? That makes it a completely different unit according to the American nutritional system. So capital C means kilocalories, essentially. Or if it just comes from a nutrition label, that's kcals. Okay? So keep that in mind as you go forward with your calculations. By the way, nutritional calories in your diet, so like your average adult needs about 2,000 calories per day. That's kilocalories, really. So you really need 200,000 scientific calories to keep your body running. That's quite a lot of energy. Okay. All right. So if you played with the demonstration looking at different types of energy, there's a solar panel option. And so I wonder, can you define, what do you think the system is and what do you think the surroundings is? Does the sun count as part of the system, or is it the surroundings? Okay, and so these are those definitions I went over briefly. These are important to know so you can decide in any given experiment when it's important to have an open system, a closed system, or an isolated system. Obviously, the solar panel would count as an open system because heat and matter can be exchanged.